This is TempleOS 5-minute random code walkthrough, episode 54, and I'm your host, Terry Davis. Let's see where we go today. And we are in multi-core load test. Okay, so what this looks like when it runs, you'll notice up here we have a 99 on core 1. Here's what it does. There are 3 different job routines, 1, 2, and 3, and they are running on core 1. Spawn creates a new task. It has the address of the task function. It has the function address and auxiliary data, the name of the task. Usually you say something like, the default is unnamed task. Anyway, then you give the target CPU. -1 means the current core. So, oops. So, the I64 parameter is, we skip that and we don't give it a name. We could give it a name right here. And then this tells it to do it on core 1. We are on core 0, and so that's on core 1. And we have a global variable, 2 global variables, one for when we're finished and one for to acknowledge that we're finished. Okay, so first we are not done, so all these stay in their loop. This one is compiling the compiler. This one is logging to the atom log. Let's see what that looks like. What is it logging? It's printing a file. It's sending a file to the atom task. It's sending itself, as a matter of fact. %F means a file, and this one is sending the it's atom logging the compiler. It's atom logging another file. So there should be 2 files in here if we unless there was starvation. There's the other file. So there's nothing to coordinate to make sure one doesn't dominate. Looks like I'm looking at the log. Anyway, so it's that easy to now the lock prefix is needed for this application, for this. As a matter of fact, there's a lock demo. If you don't lock it, this one has a task that's incrementing a global variable without a lock, unlocked. This is unlocked, and then this is with the lock. That's an assembly instruction. If you don't lock it, you lose out on some of your some of them are screwed up. So we had two cores incrementing and with one, well, anyway, so that's why you have to use the lock. So the reason the reason we don't just exit is because when this task exits, it frees the memory. This when we run this, right now it's in memory. If we unassemble job 1, so this is the code is in memory, and when I kill this task, now the code just got returned to the system and reused probably, and when it gets reused, the code is corrupted. So we want to make sure we stop the other cores before we exit and return the code. We don't want to yank the code out from underneath these other cores. The other cores need that code memory. They need that memory. So